Hello, this is John Baugh. This is CIS 2353. This week, we're going to talk about stacks and queues. Also, your midterm review has been posted on D2L, so I would highly recommend that you look over that. Your midterm examination will be the week of the 22nd. I will likely open up let's look at the dates here. The 22nd, the 20th and the 22nd, and probably the 27th will be available as days to come in during my office hours on any of those times. If none of that works out, then you should be able to we should be able to work out something with a paraprofessional or somewhere else to proctor it. So let's take a look at Chapter 8. So this week's about stacks and queues. A lot of what I'm going to be talking about will be mostly conceptual. They give a lot of examples in the book. Some of them fairly modern, some of them not so much. But we want to establish a good conceptual idea about what a stack is and what a queue is, because these are very important abstract data types that are available or that are taught in pretty much any discrete structures or data structures course. So first we'll talk about stacks. A stack is a finite sequence of elements in which only the element that can be removed is the element that was most recently inserted, or in which the only element that can be removed is the element that was most recently inserted. What we call this for a stack is last in, first out. Okay, last in, first out. So that means regardless of how it's implemented, it basically needs to provide a means by obtaining the last item that was put in. The last item that was put in is called the top. Okay, so the element most recently inserted is the next element to be removed. This is called last in, first out, or LIFO. Here are some of the methods that will be provided by the abstract data type stack. The stack ADT provides push, which means to insert an element onto the top of the stack. Pop, which means to remove the top element from the stack. So this is the removal, that's the insertion. And peek returns a reference to the element on the top of the stack without removing it. So again, the top of the stack is the element that lives at the top, of course, and then that would be the most recently inserted element. So let's take a look here. They give a little bit of a visual here. If you start with an empty stack and then push Clayton, we're assuming that at this point it's a stack of strings. You can think of a stack also as, if you think of a stack of books, I put the first book down, that's called pushing the book onto the stack, and then if I put another book on top, that becomes the new top of the stack. That's the new top that I just pushed onto the stack, and then another, then another, then another. So every time you add an item to the stack, that's called pushing, and then that item you just added becomes the top. Now, even though as human beings, and especially impatient Americans, we like, we might take a huge stack of books, like one that I might have in my office or something like that, or in my home office. I could take one from the middle of the stack and pull it out, but that's not how it works in the stack abstract data type. You're supposed to, without violating what we call the stack property, you should only be able to access the item at the top of the stack. Okay, you shouldn't be able to pull something from the middle or from the bottom of the stack or anything like that, if it's not also the top. So let's start with this example. They have a stack of strings. So let's say we have Clayton. Okay, so the top of the stack, there's only one element, so that has to be the top. That is Clayton. Let's push Eric. Well, now Eric is the new top, and there's two elements in this stack. Clayton is now the bottom, Eric is on top. If I pop, that removes the top element, so this is going back one slide. Notice we have Eric and Clayton. So what it's going to do is it's going to remove Eric and then leave Clayton as the new top, which we can see right here. There is an implementation available in java.util. However, they do recommend that people not use the stack implementation provided in java.util because it's not really it was invented long before there even was a Java collections framework, and it doesn't really fit in with a lot of things, so it can be a little bit of a pain. So a lot of people extend stack and add other features to it to make it a little bit more consistent with other things in Java. However, it is still useful. Java extends vector, which is also another pre-Java collections framework data type, but it's also virtually identical to array list, so just keep that in mind. The push, pop, and peek methods are easily defined. So if we wanted to, we could have this push, which basically returns the same item that you're putting onto the stack, and then you just call add element, assuming add element just adds it to the vector, array, etc. So how can we store the elements in the underlying array so that the average time is constant for the push method, and then how long will pop and peek take? You can take a look at that. They actually have some good discussion about that. If the underlying data structure for the stack is an array, think about how long it takes to insert an element in the front of the array. You have to push all the elements over, versus if you put the element in the back. So there's a couple different possible implementations for this. There's also a way to implement a stack using linked lists, which I don't believe they cover very thoroughly in the book. They may mention it, but I don't believe in this book they cover it very thoroughly. But that could be up for grabs for a future programming assignment. So I definitely will try to reinforce some of the topics that we cover in this chapter, even though some of them I will breeze over a little bit, and some of that's on purpose because I want you to not get too much help so that you can actually work a little and accomplish something with your own implementation of one of these, or maybe a particular program that utilizes them. So no vector methods are overridden, so it is possible to invoke methods that violate the definition of a stack. For example, myStack.remove7 will actually remove an element that is not the top of the stack, so this is kind of a big problem. The stack implementation is convenient, but unfortunately, since stack does ultimately extend vector, vector does allow random access essentially anywhere in the vector, and then stack doesn't override a lot of those, so you can actually access all kinds of different elements in the stack. However, that means that the stack that is provided for you in Java does not adhere to the formal definition of a stack purely. But if you use it just as a stack, or you extend it, or you can even use aggregation, where you make a new class with a stack as a member, and you prevent the outside world from violating the stack property, where you can only add to the top and remove from the top. If you do that, then you'll have an actual pure stack, and they actually go through a pure stack implementation in the book, I believe, as an exercise. So there are alternative implementations. You can inherit from array list or linked list, but unfortunately there's a ton of overrides you'd have to do. What about an array? Well, then where would we put the top in the array, and why? So the top would be at either the beginning or the end of the array, first index or last valid index. It would be quicker to actually put it at the end of the array, because you can just insert it without having to move over a bunch of items. So what about an array list or a linked list? All the method definitions are one-liners if we use one. Instead of inheriting from one, just use one. So then they give you the linked list pure stack. They have a linked list behind the scenes. I guess they do give you the linked list version. So you've got the linked list pure stack. You set the list equal to a new linked list. Now notice a stack is going to be the available data structure to the outside world. However, the problem, or the thing that we may want to consider, is that there's an underlying data structure supporting this stack. And that can be an array, it could be an array list, it could be a linked list. There's all kinds of possibilities. But to the outside world, you should only provide what they expect from a stack. So in this case, you've got push. All they do is they add the element and then return the element. Then they show a bunch of other implementations as well. Here's an example. Try to determine the output from the following. So they create a stack, and then from I equals 0 up to 9, so 1 less than 10, you push the items onto the stack. So the first item on the stack will be 0, then 1, then 4, then 9, etc. Right? So you get to the top of the stack, 81, and then it'll say, well, the stack's not empty. Start popping them and printing them out. So it's going to print them out basically in reverse order from what they were added in. Okay, so if you added in, 0, 1, 4, 9, 25, etc., 16, 25, etc., then it's going to pop it out and print it in reverse order. So if you ever have a situation where you need to reverse the order of something very effectively and efficiently, then a stack is a good data structure to do it. So we're not going to go through the full implementations here, but just to tell you what happens with compilers, how do compilers implement recursion using the stack. Whenever a method is called, okay, information is saved to prevent overlaying of that info in case the method is recursive. This information is collectively referred to as what we call the activation record, or sometimes just called the stack frame, okay, in the execution stack or the runtime stack. So what does the activation record, also known as the stack frame, contain? It contains a variable that contains the return address in the calling method. That's so it knows when you push it off of the stack, it knows how to get back to where it started. For each parameter in the called method, a variable that contains a copy of the corresponding argument. Okay, so we need to keep track of the data at any given time. For each variable declared in the called methods block, a variable that contains a copy of that declared variable. There's a runtime stack to handle these activation records. So you might want to ask the question, push, when the method is called. The question would be, well, what is push? Well, they're going to push an activation record onto the runtime stack. And then when the execution of that method is completed, so if main calls method A and A calls B, B will be the top of the stack. It'll keep on going, and then when it finishes, it'll pop off the stack, and then it'll return back to whatever was pushed on before it. So that's A. Then A continues until it gets popped off, and then main. So it's a very clever mechanism for maintaining where you are on the stack. Activation record is similar to an execution frame, except that an activation record has variables only, no code. You can replace recursion with iteration by creating your own stack, so just be aware of that. Okay, we're not going to go through that example decimal to binary. I do recommend maybe going through it on your own. Okay, and as a brief note, at least so you know these concepts, this may, at some point, we might do something where I make you do an implementation of one of these. So converting from infix to postfix. Infix notation is what we're familiar with. It's a notation with, we use operators that are placed between the operands that are being applied to them. And if we want to specify an override of precedence, we have to use parentheses. Well, there are other forms. It's kind of messy to convert infix to machine language, actually. So it gets messy a lot of times because of the parentheses. So what do newer compilers do? Well, first they convert the infix to postfix, and then convert postfix into machine language, because that's a lot easier. It takes out the messiness of the parentheses, because postfix actually does not require parentheses. So postfix notation, an operator is placed immediately after its two operands. Okay. So for example, in infix notation, like we would normally write it, we would say A plus B. Well, how's that written in Postfix? Well, you have A, B, and then plus. What about A plus B times C? Well, if you think about it, you've got A, B, C, but then you want B and C to be performed first, right? You want the multiplication to be performed first. So that comes immediately after its two operands. And then when you get a result from that, you have A, and then whatever the result of BC is, and then you want to add those. Okay, what about if we switch the operators here? You have A times B plus C. So A and B should be calculated first, AB multiply, right? Then you add C in. That's why it's this. So that's called postfix. Postfix means you put the operand after, or I'm sorry, you put the operator after the operands. Okay, so when you say whatever fix, infix, postfix, prefix is another one. Whenever you say that term, you're talking about where does the operator go, okay, relative to its operands. So in postfix, parentheses aren't needed. So if we want to convert an infix string to postfix, postfix preserves the order of operands, so an operand can be appended to postfix as soon as that operand is encountered in infix. So you've got the x, then a minus, so the operands for minus are not yet in postfix, so minus must be temporarily saved somewhere. We usually create this thing called an operand stack. Okay, so then you get to y and you add that to the postfix. The operands for multiply are not yet in postfix, so multiply is temporarily saved somewhere and then restored before the minus. So how would we get it to be restored before the minus, even though it came later? That's kind of unusual. Well, what would we do? Well, sounds like the job of a stack. So we'll look at that. So then you restore the minus and the multiplied and then the minus at the end. So suppose we started with x times y minus z. After moving x to postfix, the multiplication symbol is temporarily saved, and then y is appended to the postfix. What happens when minus is accessed? Okay, now what about this? Multiplication must be moved to postfix now because both of the operands for multiplication are already in postfix now. So then the minus must be saved temporarily. After z is moved to postfix, right here, the minus symbol is moved to postfix, and then we're done. Okay. So temporary storage facility is a stack. Here's a strategy for maintaining the stack. Okay, gives you a little bit of a how do we convert from infix to postfix. So I'm not going to go through the whole thing. I'll leave that up to you to do that. Here's your transition. Tokens. Token is the smallest meaningful unit in a program. Each token has two parts, generic part for the category of the token and a specific part to access the characters in the token. Okay, so for example, index 35 in a symbol table might be some identifier, and then add operation might be, for example, plus or minus. So they give you an applet that shows you some of the examples. And then they talk about prefix notation. So prefix notation is another form of notation. This is one where the operand comes before both of its operators. Okay. They show you how to convert from infix to prefix. So stacks, again, stacks are last in, first out. Okay, sometimes just called first in, last out, either way. But usually called LIFO data structures, so last in, first out. That means that the last item you pushed onto the stack is the first item that can be taken off or popped. That item that is at the or was the most recently added item to the stack is called the top. So you need to memorize what a stack is and also what push, pop, and peek mean. There's also a data structure called abstract data type called Q. Okay, Q-U-E-U-E. I know it's spelled funny, it sometimes looks wrong, and every time you spell it, you will probably think you're spelling it wrong, for a while at least. Q-U-E-U-E. A Q, don't say Quay, please. Quay or Quay. Don't make up names for it. Okay, it's just Q. It's a finite sequence of elements in which insertion occurs only at the back and deletion occurs only at the front. So this is what we call a Fifo data structure. It's like a cousin to the stack. The stack is last in, first out. The queue is first in, first out. So this is backwards from what the stack does, or it's opposite. So a queue you can think of as maybe a lunch line. Okay, a lunch line. You go in at the back of the lunch line. Let's say you have people in front of you. You have to wait on them, assuming you're not a cutter. Okay, we assume that no one cheats or takes cuts in the ideal, wonderful world of computers, computer science. So you go in the back of the queue, and then when you get to the end of the line, that's the front of the queue, and then you leave the queue, which is called dequeuing. So when you first go into the queue, they call a method called add. Generally, we call this enqueue if we're talking about the operations done on a queue. So enqueue, okay, en and then queue, name of the queue. So enqueue. Remove is pronounced DQ, okay, just like the ice cream company. So DQ, letters DQ. And then element returns the front element. So front is also another method in some languages and contexts. So in a queue, the first element's inserted. The first element that's inserted will be the first element deleted or removed from the queue. So first in, first out. You've probably heard the term printer queue. Okay, when you send print jobs to maybe a shared printer or what have you, or even you send multiple jobs, they go in, first out. So that is a queue. That's why it's called a print queue. Queue is like a line. Okay, if we compare it to a last in, first out stack, let's see what happens when we add mat. Okay, well, when you add one element to the line, or to the queue, it's both the front and the back of the queue, which makes sense because there's only one element in the queue. So if you go to an empty lunch line, you're the only person there. You maybe enter the back and then go all the way up to the front. You're the only thing in that line. You don't have to wait on anyone, and no one has to wait on you because there's no one there. What if we add Andrew to the list? Well, Andrew then becomes the back because Matt has not been taken out of the queue, so Andrew has to wait in line behind Matt. What if we want to add Samira? So Samira has to go to the back behind Andrew, who's also waiting on Matt. So this is like a lunch line. So Samira gets in line behind Andrew, who's behind Matt. Now what about remove? Okay, if we call DQ or remove, then that means Matt will leave the line. So who becomes the new front? Well, it was the previous second element in line, which is Andrew. And then Samira is still the back. So Java Collections Framework has a queue interface that includes the following three methods. Notice it's not an implementation, full implementation. It's just an interface. So it has add, which is the enqueue, same as enqueue. Remove is like dequeue. So enqueue adds at the back. Remove is like dequeue. It removes an item from the front. And then element is kind of like the corresponding method with stacks called peek. This just looks at the front without actually removing it. So it can, however, be easily implemented with the linked list class. But you still have the same basic flaw that you had with the stack class. When you invoke methods that violate the definition of a queue, for example, if I call myQueue.add 4 to location 4, add a string that is there. However, you basically just have to not call methods that violate the queue property. Okay, so you could again use it. You can implement the interface and also provide overrides as well. So we're not going to go through that. Queue application simulated car wash. This is kind of cool too. They give a kind of an interesting example if you're not clear on the things we've been talking about. But I'd highly recommend going through that. Okay. Yeah, the car wash thing is pretty long. So, okay. Well, that's pretty much it. If you have any questions, please feel free to email me or post on the discussion board, and myself and or your peers will take a look at it. Don't be afraid to post questions. If someone posts something that I think's out of line or whatever, I'll either remove it or tell everyone not to respond to it. But I've never had that happen yet, so I don't mind if you ask questions. Um, I won't accuse you of cheating unless you're trying to do something sneaky. That's kind of different. So just use the discussion board. It's there for everyone to learn. That's the primary purpose of this class. It isn't to make things difficult. It's to make everyone or help everyone learn. So if you have any questions, again, please feel free to email me. Thank you and have a great week.